Hey guys, Mr. Middleton here. Today we're looking at chords and arcs notes. At the end of this video, you should be able to understand the relationship between chords, arcs, and central angles, and you should be able to find missing lengths and justify how you got them. Okay. A chord is a segment whose endpoints are on a circle. Okay. A chord that passes through the center of the circle is called a diameter. Okay, so we've already dealt with chords this chapter. Okay, so as we look at that, that means that all diameters are chords, but all chords are not necessarily diameters. Okay, so PQ is a chord. Okay, AB is a chord, but it's also a diameter. Okay, so we talked about that here. A radius is represented by OC, right? And a radius is not a chord. Chords PQ. Okay, a radius is not a chord, so OC is not a chord because it does not have both endpoints on the circle. All right, theorem 1 with chords. Within a circle, or in congruent circles, congruent central angles have congruent chords. Congruent chords have congruent arcs. And congruent arcs have congruent central angles. Okay, so let's look at that a little bit. It says in the diagram below, circle O is congruent to circle P, basically saying that they have the same radius, they're the same size. So given that arc BC is congruent to arc DF, what can we conclude? So BC is congruent to DF. My first conclusion would be, okay, that means the arcs are the same. That must mean our central angles are the same. So maybe, or not maybe, definitely, angle BOC should be congruent to angle DPF. Okay. My second conclusion would be that, hey, if the central angles are the same, then that must mean that the chords are the same. So the chord BC should be congruent to the chord DF. It says use circle P in this next example to answer the questions. Here it says what information is given. So in this circle here, circle P, what they told us at the beginning was that arc QS is congruent to arc RT. Okay, because they marked the arcs, they didn't mark the chords here. So what can we conclude from that? Well, if the arcs are the same, we know the central angles are the same. RPT must be congruent to QPS. Angle RPT is congruent to angle QPS. And then we can also see that QS, talk about the chord here, should be congruent to RT, its corresponding chord on the other side. Chord. Okay, and that's all given from that angle. All right, let's look at the next theorem here. Theorem 2 with chords. Within a circle or congruent circles, chords that are equidistant from the center are congruent. And then congruent chords are equidistant from the center. Okay, it's just the converse of the first statement. Okay, so as we look at our first example, it says find the value of A and explain. So as we look at A, we don't know that value, but we do see the center of our circle marked here, and the distance from the center, perpendicular distance from the center to that chord A, 9, is the same distance from the center to chord PR. Okay, as we look at PR, PQ is 12.5 and QR is 12.5, so we see that PR is 25. Because PR is 25 and is equidistant from the center as A, then we know that A is 25. Okay, so our explanation is that chords are equidistant from the center. Okay. All right, or chords equidistant from the center are congruent. Let's look at number 2. It says find the value of x and explain. So as we look at x, now x isn't marking a chord, it's marking a distance from the center to a chord. And so we see that the chord it connects the center to is 36. And then we have a chord here that doesn't tell us the whole chord, but it tells us this is 18 and this is 18. So we see that that's 36 as well. Okay, so these two chords are equal to each other. That must mean they're equidistant from the center. This is 16 from the center, so this must be also 16 from the center. X is 16. Congruent chords are the same distance from the center. Equidistant from the center. Okay. Theorem 3 with chords here. In a circle, a diameter that is perpendicular to a chord bisects the chord. Diameter bisects the chord and its arcs. Okay. In a circle, a diameter that bisects a chord is perpendicular to the chord. Just the converse of theorem 3. And then theorem 5, in a circle, the perpendicular bisector of a chord contains the center. All right, so let's look at that here in these following examples. So at the bottom here, it asks us to find r, its radius, right? And so what we can see, I'm gonna zoom in just a little bit to make it easier to write and read at the same time. So as we can see here, we have Kn, which is perpendicular to Lm, okay? And because it goes through the center and it's perpendicular, we know it bisects that chord. Okay, so this is 7, this is 7. Okay, as we're trying to find r, we have a right triangle. So in this right triangle, where we have our legs of 3 and 7, we're trying to find r, we can use Pythagorean's theorem. 3 squared plus 7 squared should give us r squared. 9 plus 49 equals 58. And so square root of each, we get r equals, and it should be 7.6. So we find our radius is 7.6. And again, we got from that because a diameter that is perpendicular to a chord bisects the chord. Perpendicular to a chord bisects it. All right, number 2. They're asking us to find y in this case. We'll notice here that AC is 11 and also C, I'm just going to call it D so I can reference it, is 11. Okay, so we see from the center, BC bisects this chord AD. And that must mean that it's perpendicular to the chord. Okay, again, a diameter that bisects the chord is perpendicular to the chord. Okay, so since it does that, we have that 90-degree angle, and so we can use Pythagorean's theorem to find y and say that 15 squared, the hypotenuse, should equal 11 squared plus y squared. That's 225 equals 121 plus y squared, and that is 104. So now as we take the square root of 104, we find that y is 10.2. Again, we started that off because we know that diameter that bisects a chord is perpendicular to a chord. Okay, and last one here, we have 3, and they tell us that this line through the center is perpendicular to the chord. Okay, so we know that it's bisected. And so we can use Pythagorean's theorem because they already tell us that this is a 90-degree angle. So our Pythagorean's theorem should be set up as 6.8 squared equals 4 squared plus, so I'm going to call it another thing, and we'll call it h, okay, squared. Okay. So 6.8 squared, that gives us 46.24. 4 squared equals 16. Oops, that equals there. Plus h squared. Okay, so to get h squared by itself, we'll subtract 16 from both sides. We get 30.24 equals h squared. And now we have to take the square root of that to find our answer. 30.24, nope. And we're taking the square root of that, and that gives us 5.49 or 5.5. Okay, so we find h to be 5.5. Now remember that we relabeled this as h. In order to find x, we need to do h plus h, because x is 2 h's, and so we get 11. Okay, and a diameter that's perpendicular to a chord bisects the chord. Okay. All right, finally, it says in number 3, the distance from the midpoint of the chord to the midpoint of its minor arc. Midpoint of the chord to the midpoint of the minor arc. Let's look at that. And this seems like a tough question, but I'm going to kind of show you how it's not. They're asking us about this. How far away is, how long is this line? Okay. Again, it looks like a tough question, but it's really about understanding what part of the circle this is. We already know, well, actually, give it a try. Put in what you think that answer is. Okay. We already know what this answer is, or at least we already know what this whole line is. This whole line is a radius from the center to the side. We were already given the length of a radius here, 6.8. So if our radius is 6.8 and they told us that this is 4, it must be the rest of that 6.8, which is 2.8. Okay. All right, and there you have it. That's chords. See ya.